Electrical fuses versus electronic fuses. Electrical fuses and electronic fuses, while serving the same fundamental purpose of protecting circuits from overcurrent conditions, differ in their construction, characteristics, applications, and performance. Here's a comparison between electrical fuses and electronic fuses. 1. Construction. Electrical fuses are primarily used in power distribution systems, industrial equipment, and appliances. They are often larger in size, designed to handle higher currents and voltage levels. They can be cartridge fuses, blade fuses, or other types, and they use various materials for the fuse element and body. Electronic fuses are designed for use in electronic circuits, where they protect sensitive components from overcurrent events. They are typically smaller in size and often use surface mount technology, SMT, for easy integration onto printed circuit boards, PCBs. 2. Current ratings. Electrical fuses are available in a wide range of current ratings, from low currents to extremely high currents for power distribution and industrial applications. Electronic fuses are designed for lower current levels typically found in electronic circuits, ranging from milliamps to a few amperes. 3. Voltage ratings. Electrical fuses are designed to handle higher voltage levels commonly encountered in power distribution networks. Electronic fuses are suited for lower voltage levels often used in electronic devices and circuits. 4. Response time. Electrical fuses may have varying response times depending on their type. Some fuses are designed for fast interruption of overcurrents, while others provide time-delayed response to tolerate short-duration current surges. Electronic fuses have faster response times to protect delicate electronic components from damage. They react quickly to overcurrents to prevent thermal stress and maintain circuit integrity. 5. Resettable capability. Most electrical fuses are non-resettable. Once they blow due to an overcurrent event, they need to be replaced. Many electronic fuses are resettable, allowing them to automatically return to their normal state after the overcurrent event is resolved. This feature is particularly useful in applications where downtime must be minimized. 6. Applications. Electrical fuses are commonly used in power distribution systems, utility networks, industrial machinery, and large-scale electrical applications. Electronic fuses are used in consumer electronics, telecommunications, automotive electronics, industrial controls, medical devices, and other low-voltage electronic circuits. 7. Size and form factor. Electrical fuses are often larger and bulkier due to their higher current and voltage capabilities. Electronic fuses are compact and designed to be easily integrated into PCB designs. 8. Arc handling. Electrical fuses need to manage and extinguish arcs generated when they interrupt high currents. This can sometimes result in visible arc flashes. Electronic fuses are designed to minimize arc formation and eliminate the potential for arc flash, which is critical in environments with sensitive components. Both types of fuses play crucial roles in protecting electrical and electronic systems. When selecting a fuse for a specific application, it's important to consider factors such as current and voltage requirements, response characteristics, resettable capability, and the unique needs of the system being protected. 9. Protection objective. Electrical fuses are primarily designed to protect power distribution systems and equipment from overcurrent events caused by short circuits, overloads, and faults. Their primary goal is to interrupt the circuit to prevent damage to conductors, equipment, and other components downstream. Electronic fuses focus on safeguarding delicate electronic components, integrated circuits, ICs, and other sensitive devices from overcurrent conditions. The primary objective is to prevent thermal stress and damage to these components while maintaining the integrity of the circuit. 10. Precision and sensitivity. Electrical fuses. Electrical fuses often have a certain tolerance and may not provide the same level of precision required for protecting highly sensitive electronic components. Electronic fuses. Electronic fuses offer greater precision and sensitivity, enabling them to respond quickly to minor overcurrents that might otherwise go unnoticed in larger power systems. This sensitivity is crucial for maintaining the reliability of electronic devices. 11. Circuit integration. Electrical fuses. In power distribution systems, electrical fuses are typically standalone devices or installed in specialized fuse panels and switchgear. Electronic fuses. Electronic fuses are designed for easy integration into printed circuit board (PCB) layouts. They are directly mounted onto the PCB, allowing for compact designs and streamlined assembly processes. 12. Monitoring and feedback. Electrical fuses. Electrical fuses often lack the capability to provide real-time feedback or data on their status and condition. Electronic fuses. Many electronic fuses incorporate monitoring features, such as reporting overcurrent events, allowing for better diagnostic capabilities and system analysis. 13. Complexity and functionality. Electrical fuses. Electrical fuses are relatively simple devices with the primary function of interrupting current flow during overcurrent events. Electronic fuses. Electronic fuses can offer additional functionality beyond overcurrent protection. They might include features like adjustable current settings, selective tripping, and integration with electronic control systems. 14. Compatibility with sensitive loads. Electrical fuses. In power distribution, electrical fuses might not provide adequate protection for sensitive electronic loads due to potential overcurrent transients. Electronic fuses. Electronic fuses are designed to cater to the specific requirements of sensitive electronic loads, ensuring protection without causing disruptions or false tripping. 15. Environmental impact. Electrical fuses. Electrical fuses can generate arc flashes and heat during interruption, which may have environmental and safety implications. Electronic fuses. Electronic fuses minimize arc formation and release less energy during interruption, making them more suitable for environments where arc flash prevention is crucial. 16. Cost and implementation. Electrical fuses. Electrical fuses are cost-effective solutions for high-current power systems but might not be suitable for protecting sensitive electronics. Electronic fuses. While often more expensive, electronic fuses offer targeted protection for valuable electronic components, potentially reducing overall system costs by preventing damage and downtime. In summary, electrical fuses and electronic fuses cater to distinct needs in the realm of overcurrent protection. Electrical fuses are essential for power distribution and industrial applications, while electronic fuses are crucial for maintaining the integrity of delicate electronic circuits. Selecting the right type of fuse depends on factors such as the application's voltage, current, sensitivity, response time, and the nature of the circuitry being protected. Electrical fuses. Applications. Electrical fuses are predominantly used in high-power applications such as industrial machinery, power distribution networks, transformers, motors, and utility systems. They protect against overcurrent conditions caused by short circuits, overloads, ground faults, and other faults in high-current environments. Construction. Electrical fuses are designed to handle high currents and are often larger in size. They have robust construction to manage the thermal and mechanical stresses associated with interrupting high currents. Response time. Electrical fuses might have varying response times based on their type. Some are designed for fast interruption to minimize the effects of short circuits, while others provide a time delay to tolerate temporary overcurrents. Resettable capability. Most electrical fuses are non-resettable. Once they open due to an overcurrent event, they must be replaced. Environmental impact. The interruption of high currents in electrical fuses can generate visible arc flashes and release significant energy, which might have safety and environmental implications. Arc handling. Interrupting high currents in electrical fuses can lead to the formation of arcs. Arcs can cause thermal and mechanical stress on the fuse and surrounding components. Electronic fuses. Applications. Electronic fuses find their place in low-voltage applications, including consumer electronics, automotive electronics, industrial controls, medical devices, and more. They protect sensitive components like integrated circuits, ICs, transistors, and other electronic devices from overcurrent conditions. Construction. Electronic fuses are designed to be compact and are often integrated into printed circuit boards, PCBs, using surface mount technology, SMT. Their size and form factor are optimized for the space constraints of modern electronics. Response time. Electronic fuses have fast response times to provide rapid protection for delicate electronic components. They quickly interrupt overcurrents to prevent thermal stress and damage. Resettable capability. Many electronic fuses are resettable, allowing them to automatically return to normal operation after the overcurrent event is resolved. This feature is valuable in applications where downtime must be minimized. Environmental impact. Electronic fuses are designed to minimize or eliminate arc formation and release less energy during interruption. This reduces the risk of arc flash and damage to surrounding components. Arc handling. Electronic fuses are engineered to minimize arc formation, preventing thermal and mechanical stress on the circuit and its components. Advantages of electrical fuses. Suitable for high-power applications with high currents and voltage levels. Cost-effective solution for power distribution and industrial systems. Provides rapid disconnection to protect against catastrophic events. Advantages of electronic fuses. Ideal for protecting sensitive electronic components in low-voltage applications. Fast response times prevent thermal stress and ensure component reliability. Resettable capability reduces downtime and maintenance costs. Precise sensitivity prevents damage to delicate electronics. In summary, electrical fuses and electronic fuses serve distinct purposes in protecting different types of systems and circuits. Electrical fuses excel in high-power applications, while electronic fuses are crucial for safeguarding sensitive electronics. The selection between these two types of fuses depends on the specific requirements of the application, including voltage, current, response time, and the nature of the equipment being protected. 1. Operation and purpose. Electrical fuses. Electrical fuses are designed to protect power distribution systems, industrial machinery, and heavy equipment from overcurrent conditions such as short circuits, overloads, and faults. They function as fail-safe devices that interrupt the circuit to prevent damage to conductors, equipment, and systems in high-power applications. Electronic fuses. Electronic fuses are tailored to safeguard sensitive electronic components, integrated circuits, ICs, and other low-voltage devices from overcurrent events. They serve as precision protection for fragile electronic components, preventing thermal stress, and maintaining the performance and integrity of electronic circuits. 2. Size and form factor. Electrical fuses. Electrical fuses are often larger and bulkier due to their capacity to handle higher currents and voltage levels in power distribution networks. They are commonly found in industrial switchgear and distribution panels. Electronic fuses. Electronic fuses are compact and designed for integration onto printed circuit boards, PCBs. They have a surface mount design and small footprint. These fuses allow for miniaturization of electronic circuits, making them suitable for consumer electronics, telecommunications, and automotive applications. 3. Current and voltage levels. Electrical fuses. Electrical fuses are designed to handle high current levels and elevated voltage levels that are typical in power distribution systems and industrial applications. They can interrupt fault currents of several thousand amperes and higher. Electronic fuses. Electronic fuses are optimized for low to moderate current levels typically encountered in electronic circuits. Current ratings are usually in the range of milliamps to a few amperes. voltage levels are lower and more in line with the operating voltages of electronic devices. 4. Response time. Electrical fuses. The response time of electrical fuses can vary depending on their type and rating. Some fuses offer fast response times, while others provide time delay characteristics to accommodate temporary overcurrents. Electronic fuses. Electronic fuses offer extremely fast response times, responding within microseconds to protect sensitive components from overcurrent events. Their quick reaction prevents thermal stress and potential damage to delicate electronics. 5. Resettable capability. Electrical fuses. Traditional electrical fuses are non-resettable. Once they blow due to an overcurrent event, they need to be replaced manually. Electronic fuses. Many electronic fuses are resettable, referred to as polymeric positive temperature coefficient, PPTC, or resettable fuses. They automatically revert to their normal state once the overcurrent condition is resolved. 6. Arc handling. Electrical fuses. Electrical fuses may produce visible arc flashes when interrupting high currents. Arc handling and extinguishing are important considerations. Electronic fuses. Electronic fuses are designed to minimize or eliminate arc formation during interruption, reducing the risk of damage to sensitive electronics and adjacent components. In essence, electrical fuses are the workhorses of power distribution and industrial systems, protecting against high current and high voltage faults. Electronic fuses are precision components engineered to shield delicate electronics from overcurrent events with fast response times and minimal disruption. Choosing between the two depends on the application's voltage, current, sensitivity, response time, and the nature of the circuitry being protected. 1. Core purpose and application. Electrical fuses. Electrical fuses are designed to safeguard power distribution systems, heavy machinery, and industrial equipment from high current overloads, short circuits, and faults. They find use in environments where the primary goal is to protect against catastrophic failures and maintain the integrity of power transmission and distribution. Electronic fuses. Electronic fuses are specialized to shield sensitive electronic components and integrated circuits, ICs, from low current overloads and faults. They are vital in environments where precision protection is essential to prevent minute changes in current from affecting electronic performance and reliability. 2. Current and voltage levels. Electrical fuses. Electrical fuses handle substantial current levels, often ranging from tens to thousands of amperes, making them suitable for high-power systems. They are equipped to manage high-voltage environments encountered in power distribution. Electronic fuses. Electronic fuses are designed for circuits with much lower current levels, typically in the milliamp to ampere range. They cater to the lower voltage requirements of electronic devices, preventing damage to sensitive components. 3. Response time and sensitivity. Electrical fuses. Response times of electrical fuses vary depending on their design and characteristics. Some may have relatively longer response times. They might not offer the precision required to protect sensitive electronics from rapid current changes. Electronic fuses. Electronic fuses possess ultra-fast response times, acting within microseconds to prevent thermal stress on delicate components. Their sensitivity ensures that even minor overcurrent conditions are promptly addressed, maintaining the health of the electronics. 4. Form factor and integration. Electrical fuses. Electrical fuses are typically larger, necessitating dedicated spaces in electrical panels or enclosures. They are standalone components that need to be placed strategically in power distribution systems. Electronic fuses. Electronic fuses are designed for compactness and are often integrated directly onto printed circuit boards, PCBs. They seamlessly become part of the circuit layout, allowing for efficient use of space and streamlined manufacturing processes. 5. Arc handling and disruption. Electrical fuses. Interrupting high currents in electrical fuses can lead to visible arc flashes and release substantial energy, potentially causing damage. They must incorporate arc handling mechanisms to ensure safe and controlled interruption. Electronic fuses. Electronic fuses are engineered to minimize arc formation and energy release during interruption. This feature is crucial to protect sensitive components from damage and to avoid disrupting nearby circuits. 6. Resettable capability. Electrical fuses. Traditional electrical fuses are typically one-time use devices and need manual replacement after an overcurrent event. Electronic fuses. Many electronic fuses are designed with a resettable feature. Once the overcurrent event is resolved, they automatically return to their normal state, minimizing downtime. 7. Complexity and features. Electrical fuses. Electrical fuses are relatively straightforward devices, with a focus on interrupting current to prevent damage. They are well suited for high-power applications where simplicity is an advantage. Electronic fuses. Electronic fuses can be more sophisticated, offering additional features such as adjustable current settings, monitoring capabilities, and integration with control systems. 8. Cost considerations. Electrical fuses. Electrical fuses are cost-effective solutions for protecting high-power systems, making them essential in industrial and utility contexts. Electronic fuses. Electronic fuses might have a higher cost due to their precision and sensitivity, but they provide invaluable protection to sensitive electronics, potentially preventing costly failures. In summary, electrical fuses and electronic fuses cater to different realms of overcurrent protection. Electrical fuses excel in high-power scenarios, while electronic fuses are essential for safeguarding electronics. The choice between the two depends on factors such as the application's voltage, current, sensitivity, response time, and the nature of the circuit being protected.